Hello, everyone. Thank you for coming, and thank you for people that came on Zoom. Today we are going to give our third lecture. This time Alexander Krikun will speak. And the first two times we spoke about something that is very small, which gives you quantum mechanics, and something that is of a lot of things together, which gives you statistical physics. Today we are going to speak about something that it's moving quite fast, and we will learn hopefully that things have different perspective, not in real life but also in physics. So two observers will not agree if they move with respect to one another. So welcome to lecture number 3. Sasha, please.
Yeah, thank you, Dima. Welcome, everyone. So this is actually a very interesting discussion of now. Yes. Yes. So I was about to say that this is a very interesting discussion of the different perspectives, but at the same time, the laws of nature, which are the same for everyone. And I would like to start with a prelude to this lecture, saying that, so the title here, we are talking about the adventures through the laws of nature. We as physicists, we care about laws of nature very much. Why do we? So first of all, the fact that there are some laws underlying some processes, some behavior of things in nature, it allows us to study some general behavior instead of studying every single phenomena separately. So if there is a law so that everyone obeys it, then it is enough to study a law, and then this will allow you to make predictions about how things behave. If there are no laws, or if there are laws that someone does follow, someone doesn't follow, then we are hopeless as physicists, because if we study a couple of systems, we can say nothing about the behavior of the next system. So we cannot predict things. And also, not only we cannot predict things, we also have real problems understanding what's going on around, because the best we would do without laws is to tabulate, to study every single system separately, and no more than that. So it is actually a big luck for us that there are some laws in nature, and we can formulate some simple things, some simple relations which different things follow. And that gives us first the ability to understand how our world works, but also the ability to predict how things will behave, those things which we don't know yet. Of course, there are options always that the laws which we thought we understand, they are different, but not exactly the same as we thought. So learning about new things forces us to correct the laws which we use. But nonetheless, in physics, this is the primary goal which people put for them, finding the law, and such a law that everything will follow. And today we're talking about special relativity, and special relativity is a beautiful example of this thing. So this is the theory, and this is the law of nature, which can derive almost completely theoretically without looking at anything, just by requiring that some things, some laws are the same for everyone, for every system in nature, and it doesn't depend on how fast the system is moving. And now, so special relativity was formulated in 1905. Now, when Dima asked me to give a popular lecture about it, I was almost confused because I couldn't understand how can you explain the thing which is so natural and so basic. Because now in theoretical physics, special relativity is like everywhere. This is the way we think about things. This is the way we write equations. So it's over more than 100 years. It evolved from a very ambitious idea via numerous experimental confirmations to the very basics of our understanding of nature. And what's beautiful about it is that it can solely be derived from just requiring that some laws, actually all laws of nature, are the same for all observers, so for all things, independently of the velocity which they move. I will try to explain it to you using only fingers. And it is actually surprising that such a convoluted actually theory, something which is not really doesn't really follow our everyday experience. It's puzzling. Yet it can be explained quite simply. I will only need one formula, strictly speaking, two, but on the same slide. And I will let you know when it appears. So what we are talking about today, we'll start from discussing what does it mean, the equality of things in before the laws of nature, that like the laws of nature must be the same for everyone. Otherwise, these are not the laws. So there shouldn't be exceptions. There shouldn't be special systems or some special class who doesn't follow the laws. This is, I mean, in some other areas of existence, this is possible, not in physics. So we'll see that this requirement of equality before the laws of nature requires us to put the absolute speed limit for the things, how they can move. And this is the speed of light. This theory, introducing the speed of light, allows us to put some very interesting relationships between space and time. So it was the first moment in the theory and philosophy when people started thinking about the space and time in the same terms, which already sounds a bit puzzling from our everyday experience. Finally, given this geometry, which arises from the requirements of special relativity, we will see that the geometry gives some predictions, some physical effects, which are also quite puzzling from our everyday experience, but they are necessary if we want the laws to work the same for everyone. And despite the fact that you might think that since we're not moving with the speed of light in our everyday lives, and we don't see anything which moves with the speed of light except light, yet there are numerous applications of these things in our everyday lives, which we use every second, but maybe not quite appreciate. But let's start from something simple. So as I said already, the laws may evolve in time. So the first law which I would like to point out is the law of inertia by Newton. So this dates back to the end of 17th century. And here's the original formulation, which is a bit cumbersome. So the motion of bodies included in a given space are same among themselves, whether that space is at rest or moves uniformly in a straight line without circular motion. What does it mean? So imagine there is a person in a train, this guy, and there is another person on the station, yeah, the other guy. So these people, they're not alone, of course, in these spaces, right? So here you see some given space. So some objects are around, I don't know, a cup of tea or maybe other people, and they interact with each other in the same way. So this guy drinks his cup of tea in his train, and this guy drinks his cup of tea in his house. But the laws which they experiences are pretty much the same. It's the same cup of tea, it's hot, it's sweet, whatever. So what follows from this law is that since the mechanical things behave in the same way in these two different systems, we will call them frames, there is actually no way for me to figure out whether I'm sitting in the train or whether I'm sitting in the house. Because my experience from the objects which are surrounding me is exactly the same. They follow the same law. I have a beautiful demonstration for you how it feels basically when you don't know exactly whether you're moving.
Решил сделать комнату в виде железнодорожного купе. Ну, пойдемте туда. Вот, заходите. То есть должно же что-то мелькать, и вот я вместо окна взял и забабахал плазму огромную, 50 дюймов. И все. И вот в чем бонус, да, то есть, во-первых, если вдруг приезжает куча гостей каких-то.
So you see, as long as you're sitting in this room and you're looking out of the window, you have no idea whether you are inside the house because it's a good plasma and it has nice sounds. But just sitting there drinking tea, you will never figure out that you're inside the house. So it doesn't matter. That tells us that Newton was actually right. Of course he was right. He didn't just conjecture this law, that was derived from his experience. And that tells us that indeed mechanical laws are the same in different systems as long as these systems are in uniform motion against each other. So basically it is quite important that this train is moving constant speed. It doesn't accelerate. Because if it would accelerate, then you would maybe spit out your cup of tea. But these two systems, whose relative motion has constant speed, they called inertial frames. And the modern formulation of the Newton's law is that the laws of mechanics are the same in all inertial frames. So it doesn't matter how fast things move, as long as they move uniformly, the laws are the same. But yes, and we can actually look at all the processes from two different perspectives, because we know that the laws in the train are the same as the laws in the station. That means that it doesn't matter who is looking, you will still experience the same physics. So here I have the two plots for you. So one is from the point of view of the station. The station is, so this graph shows the time at the station and the length, which is measured with respect to the station. So we see that the blue person is just sitting there. It has velocity 0. So its coordinate, its position against the station doesn't change with time. So at any moment, it's in the same position. But the red guy who is moving, he's changing his relative position to the station all the time. So we see that at earlier times, he was like before the station. At later times, he was crossing the station. At even later times, it is on the other side of the station. So this plot is very useful. This is called the space-time diagram. We are going to use it a lot. But absolutely the same set of things can be described from the point of view of the person in the train. So this is the red plot for you. So this is related to the train. We see that now the red person inside the train is sitting still. So basically its position with respect to the train is the same at any moment of time. But the person in the station moves, and he actually moves the opposite direction, right? So at earlier times, the station is to the front of the train. Then the station passes the train, and then the station is behind the train. So the train leaves the station behind. So this plot shows how I'm sitting at the station, looking out the window and see how the train passes by. This plot shows that I'm sitting in the train, looking outside the window and see how the station passes by. But it's the same process. The train passes by the station. Okay, let's make it a little bit more complicated, right? So we can actually interact between these two systems. So suppose suppose this is a postal train, and this is a post office on the station, and I need to deliver a parcel to the station, but I don't stop. This is possible, actually. This is how people do, at least did in the 18th century. So I can throw the parcel out of my train so that the person at the station catches it. We have the same two plots here. From the point of view of the station, there's a guy in a train who is passing with quite high speed, and then it throws out the parcel. And this parcel, look at this, it is almost vertical. So basically, the parcel almost doesn't move, just catch it. But from the point of view of the person in the train, I'm sitting still, the station passes by, and I throw parcel to the station with a speed which is enough for the parcel to reach the station. Interestingly, the speed of this parcel from the two different points of view is different. So if I'm sitting on the train, I really need to push hard to throw it fast enough with the speed W so that it reaches the station. But from the point of the person at the station, the parcel arrives with the velocity v minus w. So that's the difference, which can be as small as 0 if I'm sitting in the train, if I'm really careful with measuring my speed. I mean, there could be porcelain in the parcel, so I want to be careful. But look at that again. So these are mechanical actions, and they don't differ from the different point of view. So the parcel leaves here, arrives there. It leaves at some moment of time. It arrives at some other moment of time. And it's all okay. But for this to happen, for this to work, the velocity of the parcel must be different in two different frames, two different systems of measurements from two different points of view. So mechanical laws, they don't postulate any velocity. Velocity can be anything. So this is not a problem for us. The laws, they don't include velocity, mechanical laws. So that's why it all works. But now we are living in 21st century. So mechanics is not enough. What we actually would like to have in a train is Wi-Fi. And Wi-Fi is not a parcel. It's not handed. It travels as an electromagnetic wave. And electromagnetic waves, they travel with the speed of light, because light is electromagnetic wave. And there are Maxwell laws, which are separate from laws of mechanics. And these laws predict that there are electromagnetic waves. So we can see that if the electric field oscillates, and there is also magnetic field which is oscillating. And the speed with which this magnetic wave travels is fixed. It is speed of light. It's always the same. It follows from the laws of Maxwell. So we suddenly found a law which postulates some speed, which was not the case for mechanics, but it is truly the case for electrodynamics. So if you want your Wi-Fi to work in the train, you want the laws of Maxwell, the laws for electrodynamics, to work in the train in the same way as on the station. And here we open the can of worms. Because look at this. Now, let me think that I'm not throwing a parcel. I'm sending an email from my train to the station. So here's the email. And now we understand that if we want the laws of electromagnetism to be the same from all points of view, then the velocity with which this mail travels must be the same in both points of view, must be the speed of light. So I take my diagrams, I can basically draw what happens, right? So from the point of view of the station, there is a train passing, there is a red guy in the train, sends a message. The message is sent at this point, it arrives at the station at this point. It's all okay. From the point of view of the train, again, I'm sitting in the train, I see the station coming to me, I send the message, and the message reaches the station at a later point. But compare the time, because the speed of light in this from these 2 points of view is the same. Just drawing these diagrams, so the speed here is just the inclination of the straight line, right? So there is no way I can draw these two diagrams so that the point where the message is sent and the point where the message arrives happens at the same moment in time. Something is wrong with time now. So if we require the absolute velocity, which doesn't depend on the point of view, that requires us to abandon the concept of absolute time. So the old law of Newton, which said that time is absolute for everyone, is now substituted with a new law that is not time, it's the velocity of light, which must be the same. So again, the velocity must be the same, just because electromagnetic laws are the same. So nothing more than that. Well, that's okay. Maybe time is not so bad, right? Well, who cares? But there are strange things happening. So firstly, and this is also a problem of time. So now when the time in the train and the time in the station are not exactly the same thing. Also, the notion of two things, two events happening simultaneously is also not the same. So now imagine again, there are now three persons: blue guy, green guy, and red guy. So the green and red, they are in the same train, but they are lazy, and one is sitting in the front, another one is sitting in the back, and they are texting both of them to the person at the station. And there is a I don't know, some table in the train, which is exactly in the middle, which says that the next station is the station of the blue guy, right? And both of these people want to text him at the moment when they see that the next station is going to be this. They will text him simultaneously from their point of view, right? Because this sign is in the middle of the train, of the carriage. And the distance between one of them and another of them to this sign is the same. So they will see this sign at the same moment. It is shown on this diagram, right? So here the signal starts. It reaches with the speed of light, both of them, from the point of view of the train. This is okay. This is simultaneous. But if I draw the same process from the point of view of the station, I will be surprised. So here again, these are two guys, the red one and the green one, who travel with some speed inside the train. There is this signal in the middle of the carriage, which travels to one of them and another one of them with the speed of light. But because one of them is running away from the signal and another one is catching up with the signal, the signal will arrive to green guy earlier than to the red guy, because the speed of the signal is still the same in both of these systems. So even this event of those two guys sending a message will not be simultaneous in this station point of view. So simultaneity is also different. So in the train, the two things might look like simultaneous, but from the station point of view, they are not anymore. Well, maybe simultaneity is also not so important, right? What is important for us? Well, one thing we cannot abandon, and this is causality. So basically, if something is the cause for something else, which is an effect, this should be the same no matter what is the point of view, right? So I don't know if right, if the green guy sends a message to the red guy inside the train saying that he leaves the next station, then the red guy, knowing that the green guy leaves at the next station, will also leave. If he doesn't get this message, he will not leave. So the red guy leaving or not the train is a result of the green guy sending a message. So this is what we call a causally connected events. So the red guy gets the message, this is the reason, this is the result, and the green guy sends the message, this is the cause. And the result should always follow the cause. So as long as they are not moving too fast, I can draw the diagram from the station point of view, where also like these guys, two of them are moving, the signal is traveling with the speed of light, the green guy sends the signal and the red guy gets the signal. So okay, so at least, I mean, maybe the time is a little bit different, right? Maybe something is not simultaneous, but at least the result is followed by after the cause. But now let's just think about, okay, that could be a fast train. What if this is a really fast train? The train which travels faster than the speed of light. No one told us before that it's impossible, right? It should be, okay, fine. I mean, we just wait and we maybe pay a little bit more for the ticket to get really fast train. But look at this. Inside the train, the green guy sends a message to the red guy, the same story. But from the point of view of the station, we really get something which cannot be interpreted in any way. So these two guys are traveling with a speed which is faster than the speed of light. So basically they are, these curves at every single moment of time, they move in their coordinates more than the signal which travels with the speed of light, moves. So when the green guy sends a message, the message just goes somewhere else. I mean, it will never reach the red guy. It will never catch up with him because this red guy is moving faster than the speed of light. So if we allow those guys to move faster with the speed of light, we break causality. And this is something which we cannot afford, because if one thing is the reason for another thing, it shouldn't matter from which point of view we're looking at this. Because, you know, so these are not, these two diagrams are not two diagrams of two different processes. This is the same process. It happens. It happens inside the train, but from the point of view of the person at the station, cannot happen at all. So there must be something universal. Okay, the truth is the same, no matter what is the point of view. So that brings us to a very important consequence of the equality of laws of electromagnetism for everyone. The consequence is that no relative motion with a speed faster than the speed of light can be allowed. So there is a universal speed limit. if one object is moving relative to the other object, the relative speed cannot be faster than the speed of light. If it is faster than the speed of light, then there could be events which happen or not happen depending on your point of view, which cannot be the case. So what is this maximum speed? I mean, how seriously does it affect our lives? So here's the speed limit. Can we live with that? And also, what does it exactly mean? So suppose I'm already moving quite fast, right? Can I just, as usual, I mean, if I move just 10 kilometers more, I will not get a fine, right? So, yes, that's important. That's important. So the laws of nature are not like human laws. You cannot exceed the speed of light. If there is a speed limit, this is a speed limit. Why? Because suppose I have a rocket with a thruster and infinite supply of fuel, and it just accelerates, right? I have constant force which accelerates all the time. If it would be a Newton universe with the Newton laws everywhere for all the speeds, then I will just constantly accelerate, and my speed, depending on time, will just grow linearly. But here's unity. This is the speed of light. And the special relativity tells me that I cannot exceed the speed of light anyway. Apparently, indeed, if I just keep accelerating, the gain in speed which I will get will be smaller and smaller. The faster I get, it is harder for me to accelerate. That's why I will only approach the speed of light, but I will never reach it. This is how speeding in special relativity looks like. You can push your thruster more, but you will never exceed the speed limit. But that's fine. That's fine for us because the speed limit is really high. So there is an exact number. This number here is not exact, but let me just bear with this. The exact number is 2997, and etc. So the speed of light is really high. It is 300,000 kilometers per second. None of us here moves with this speed. So no cars move with this speed, no trains move with this speed. So we don't really, maybe we shouldn't care, right? The fastest ever built object, the object built by humans, the spaceship Parker, it only travels 163 kilometers per second. There's a long way to go. So this is only 500% of the speed of light. So nothing which we build, no material objects move any faster. And it actually, this is the thing which every year updates the record of speed. So we are living in a very interesting moment now that the record of speed is rising every time because this probe is orbiting sun. It goes in circles, and every other circle it comes closer to the sun, and it gets into the atmosphere of the sun. And the closer it gets, the faster it gets. But it will not reach the speed of light. On the scales of Earth, the speed of light is also ridiculously fast. So I mean, it's like summer is coming, and we want to go to Tenerife. I mean, every one of us, I believe. If we use a car, it will take us like 74 hours. And this is not realistic, really, because we also need to take a ferry and etc. But if we use the photon transport, this option here, it will only take 70 milliseconds. 17 milliseconds and you're in Tenerife. Could be quite nice, isn't it? So this is just amazing how fast the light travels. But on the scales of the solar system, for instance, this speed is already easier to understand. So basically, the distance between Earth and Sun is big enough. This is not 5,000 kilometers. This is 150 million kilometers, the distance to the sun. And it takes for light from the sun to travel to Earth whole 500 seconds. This is a little bit more than 8 minutes. So the light which comes now here to the surface of Earth, it was emitted at the surface of the sun 8 minutes ago. This is the speeds, and these are the distances which are commensurate to the speed. But actually, on the same time, I mean, if you really feel pressured by these speed limits, then you will appreciate that actually the speed of light is not so high. I mean, it depends on point of view, right? So the closest star, the star which is closest to the sun, is separated this distance from us. I'm not going to read this number. Many zeros. But if you just divide it by the speed of light, which is also a big number, right? You will get 4.25 years. So the light ray travels 4 years from this star to us. And this is disappointing because if we would like to travel to this star, it cannot be faster than that. So just leave with this. An exercise for those of you who have a calculator. Calculate how much distance light travels in 1 year. This is a very useful unit of length on cosmological scales, which is called the light year. So the light travels in a year. To compare, right? So the distance to the closest star is 4.25 years. But our galaxy, Milky Way, 100,000 light years. So like all these stars which will only reach in a year from now, I mean, they are indistinguishable as pixels here. This spectacular that recently, I believe many of you know, astronomers were able to take a picture of the black hole, which is located in the center of our galaxy. And this black hole is 25,000 light years from us. So this light which we get, and this is not really, I mean, it's not even light, this is radiation. It was emitted 25,000 years ago. We don't even know, I mean, whether this object exists anymore. It could explode the next year. We don't know about it because the light took so much time to travel. But also, I mean, okay, this could be disappointing, right? That we cannot move really fast. We cannot explore our galaxy on a car, I mean, on a fast car. But the fact that the speed of light is finite not only puts limits, I mean, actually speed limits are useful, right? So, I mean, they help us to be secure on the roads. But for us, as people driving the cars, navigating, the fact that the speed of light is finite and constant, independent on the frame of reference, is very useful because this is the reason why GPS navigation works. So there are satellites which orbit the Earth, and on every single satellite there is an atomic clock which measures time very precisely. And what these satellites do, they every second, every millisecond, they just send a signal saying what time is it now according to my clock. A person who gets the signals gets the signals with different delay because there is different distance from different satellite. So when I get the signal from this satellite, some time passes, and knowing what time was when the satellite released the signal, I can calculate the distance. And if I calculate the distance to the 3 satellites, it triangulates my position, and I can figure out where I am on Earth. There is a caveat here. So right now we get upset if our GPS navigation precision gets more than 10 meters. And this is This is really ridiculous, because if you want to measure the distance with accuracy of 1 meter, for instance, you need to measure time with accuracy of 3 nanoseconds. It's an extreme accuracy, and the atomic clocks which orbit the Earth, they can do this. They can provide such an accuracy for us. But when you want to measure it with such a precision, you need to take care all possible corrections into account. So this is not an easy business. Yet, this is only possible because speed of light is finite. Right. Before we go to the break, let me come back to this space and time diagram which we discussed at the very beginning. So now we have the limit in speed. So we just said that nothing can move faster than the speed of light. So here on this diagram, these yellow lines, they are crossing the diagram at 45 degrees angle. And every moving object may train with the rocket thrusters or some other object which is just wandering around. They can only move with the speeds which are lower than the speed of light. That means that they are closer to the person who just standing here still. Nothing can move with the speeds faster than that. And that allows us actually to define what is past and what is future. So remember I told you about causality at the very beginning. So we wanted to fix the problem of causality by introducing the speed limit. So now when we have it, causality is really feeling well because, because if I'm standing here, there is only limited number of events, of things which I can affect. If I start sending signals in all possible directions, only people who are at this moment located in this region will actually get this signal. So this is only this region we can affect by, which is affected by my existence now. So roughly speaking, my future, whatever it is somewhere here. My future cannot be there in this region, which is shaded, because nothing can travel faster than the speed of light. So no matter what I do, the person who is sitting at this point, for instance, will not know about the fact that I exist, because it is too early for this person to know. So we can actually, given the speed of light, we can now define the absolute future and the absolute past. There are only a finite number of events which I can affect by doing anything. So my future is lying somewhere here. But there is also a finite number of events which could affect my life now. So something which happened in the past can only affect my life if it happened close enough to me. So something which happened in the past, but far enough, cannot affect me because the signals could not reach me at given point. And it doesn't matter what kind of signals. It could be light, could be gravitational waves, could be parcels with porcelain. Nothing can move faster than the speed of light, because we want the speed of light to be the same for everyone. And with this, let me call for a break, because there is some math ahead. Yeah, so
before you go to the breaks, are there any questions? Okay, so we go for the break, and so when we meet in 15 minutes, let's meet at 7:05 in 20 minutes. Attention everybody. Math is ahead.
Behold. Okay, now with fresh forces filled up with coffee, tea, and bupule, so what we just reached so far. So we required, I mean, like there was not so much to require. Like, we just wanted our Wi-Fi train. So we required that electromagnetic laws don't depend on the inertial system when they're measured, where they're measured. Inertial systems are the systems which move with a constant velocity with respect to each other. So it's a special class of systems, but let's at least require for those. And we saw that because of this requirement, we're forced to require that the speed of light is the same in every inertial system, no matter what is the relative speed. Because the speed of light is a part of the laws of electromagnetism. But now we see that if there is a speed which we require to be the same in all the inertial systems, then this speed must be the maximal possible speed of motion. Because otherwise we break causality. So we arrived at the statement that somehow so what is speed, right? Speed is the relation between length and time, which is constant, absolute, like the same in all the inertial systems. So that requires us to somehow understand how the space and time are related in such a way that there is this constant speed, and that I can change the point of view, go into different inertial systems, and the speed will be the same. So somehow, as we saw at the very beginning, so something happens with time. We will also see that something is happening with space. So they are related. They are related by the speed of light. Now, speed of light is more fundamental than space and time. But in order to understand this, we need to recall how to measure distances in geometry. So those of you who have been in school may remember that if I have a normal plane, which is called the Euclidean space, and I measure the distance between 2 points, which are separated in x and y coordinates, then the distance is given by the Pythagorean theorem. So the length of the hypotenuse of the side of the right triangle is a sum, well, the square root of this length is the sum of squares. Oh, wait, the length is the square root of the sum of squares of the sides of the triangle. This is, I mean, this is easy enough. I don't need to speak more about that. But on this plot, what is quite important for us is that the points which are separated from the origin with the same distance, they form these circles. So basically, in every single point of this circle is the same distance from 0, because if I take the point and then I sum the square of x and the square of y, I will get the same number for all of these points. And so say all these points are separated distance 1 from the origin. This is distance 2, 3, and etc. These are circles. But when we start talking about space and time, they behave in different way. So we already understood that basically space and time, they belong to like the same geometry, which is called space-time. That's easy to remember. And one can actually develop a geometry on this space-time. The only difference which one need to make is that instead of a sum of squares here, I need to take a difference of squares. So if I want to measure distances in this what's called pseudo-Euclidean geometry, I need to take the distance squared in x and subtract the distance squares in time. So what is distance in time? The time is measured in seconds. Distance is measured in meters. How can I do that? Of course, now when I introduce the absolute speed of light, I can multiply my time by c, the speed of light, and it will give me some meters. It will not depend on what I'm talking, like what the process I'm talking about, what's my point of view, because c is the same all the time. And in this geometry, if I assume this measure, this way of measuring distances, I will see that these circles, which had the same distance to the origin, are now turned into hyperbole. So you can basically figure out if I fix s to some value, then x will depend on time on t as a hyperbola, and we see that this hyperbole here, they have x which is bigger than t. So for this hyperbole, s squared is positive, and for this hyperbole, s squared is negative. And this is okay. S squared is negative is not a big problem, even for a mathematician. But what it gives us, this new measure, gives us a very special role of these light rays. So remember, I was already putting them on my plots. So this is the particle which moves with the speed of light. So apparently, it also separates these hyperboles from these hyperboles. So this is a part of this geometry. This is a feature of geometry. And it will be the same in all the geometries which are described by this formula. So this pseudo-Euclidean spacetime is really the mathematical way to encode the fact that we have a very special speed, which is the same from all the points of view, and nothing can move faster than the speed. So in order to include this in mathematics, we need to change this plus sign to this minus sign, and this is it. Well, okay. Suppose I believe you, me. Now, what kind of consequences follow from this new mathematics, from this new geometry? So now, instead of just talking about space, which has directions here, there, left, front, and top, there are 3 dimensions. And all these 3 dimensions behave in this Euclidean nice way. So if I want to measure distances, I just sum squares. I included in our world the 4th direction, time, in which we all propagate all the time. So actually, every one of us, even if we stay at the same point, we are moving in some sense in this on this plot, because we are staying at every point of time. We are staying in the same coordinate. So basically, now we can include this new dimension in our geometry. The only modification is that this geometry comes with minus. What are the consequences? Yeah, let me stress it again. This is the law. This is the mechanics of how time is now related to space. This will tell us how time changes when we change the point of view. This is it with mathematics. So just remember this. Remember this picture. Good. So now having this hyperbole at hand and having this new geometry, I can avoid plotting 2 pictures for you every time. So now the 2 points of view, the blue guy and the red guy, can be plotted on the same cartoon, but they use different points of view, or we can say that they use different inertial frames, and these frames have different coordinates. So basically, we already learned that, right? That this blue guy measures his own time. This red guy measures his own time. So the time of blue guy is this blue arrow. The time of red guy is this red arrow. They also measure space differently. So in the space of blue guy, the red guy is moving. In the space of red guy, the blue guy. So look at this. In the space of the red guy is not moving, standing on the same coordinate. So if I put his length coordinate on this plot, which is a little bit inclined, his position in this coordinate, and we know that it actually travels along this line, right? So he has some speed from the point of view of blue person. So this is a bit inclined. That's the same as on the cartoon a few slides ago. But his coordinate on the red axis doesn't change. So basically his coordinate on the red axis is always 0. That's why this red line is the time axis of his moving frame. So what's the difference between this plot and this plot here in Euclidean geometry? So if in the Euclidean geometry I change the coordinate system, the thing which I will see is that this axis moves some angle and this axis also moves some angle. So they will rotate by the same angle on one side. But if I rotate this system, this hyperbolic system, the two axes rotate in opposite directions. So the faster is your speed, the closer is your trajectory to the light ray trajectory, and the closer is your space coordinate to the light ray trajectory. This is very interesting because if I will include, if I will consider the inertial frame of the person which moves with the speed which is very close to the speed of light, you see what happens. These two axes, they almost collapse on light of ray, ray of light. But recall about those hyperbole, right? So if I talk about my Euclidean geometry and I rotate the axis, the way I can measure distances is by checking where my axes cross this circle. So basically, if my axis is rotated with some angle, then I will be able to grade it in the same way as the original axis if I just put the dots where the axis crosses these circles. The same applies here with hyperbolic geometry. So basically, if like on this red axis, 1 second passes in from the point of view of this red guy, when this red axis crosses this first hyperbola. Then the second is here, the third second is there, and the fourth second is there, and so on. You see that if my axis gets closer and closer to the light ray, because it's hyperbole, they run away. At the light ray, these ticks on this axis will become further and further separated. Basically, 1 second from the point of view of this red guy will take longer on this picture, on this axis. And that leads us, well, okay, yeah, that will lead us to some interesting effect, but not yet now. Before that, I should convince you that in my inclined rotated coordinates, there is no more confusion about simultaneity, which we discussed at the very beginning. So recall this situation, this experiment, which we discussed at the very beginning. There are two people in the train, and there is some sign flashing, and they send signals at the same time. So from their point of view, they do it at the same time. But from the point of view of the person at the station who gets these messages, he sees that they did it at the different times. So here, this picture is from the point of view of the station person. So we have blue axis, and the red and green guy, they travel with some speed. And what we already saw in one of the previous slides is that the light which reaches red guy and green guy, from the point of view of the station person, reaches them at different points of time. So you see on this blue axis, these are two different moments of time. But now I have this red axis, so the axis of the moving train. And you see that because in red axis, the time of the red axis is inclined, but also the space of the red coordinate system is inclined. These two events are located actually at the same moment of time, because in order to measure this time, I need just to project them along the x-axis to this tick. So basically now, when I introduce these rotated coordinates, I call them rotated, but they are really actually collapsed around the ray of light. I can describe the two different point of view on the same picture. So from the point of view of blue person, these two events are different in time. From the point of view of red person, who uses different axes here, these two events are at the same point. So it's useful. I don't need the second picture here. But now, yeah, let's talk about this hyperbole a little bit more. So we have clocks, and as we discussed, because of this absolute speed of light, we had to abandon absolute time. So now every single person has its own clocks, and well, which is of course usual, but these clocks are not running with the same speed. The blue guy has his clock ticking every blue point here. So this is 1 second, 2 seconds, 3 seconds, 5 seconds. The red guy has his own, and the clock also measures seconds. But from the point of view of this diagram, these seconds, as I already explained, they are lying on the same hyperbole, because this hyperbola basically shows all the points which are 1 second away from the origin, right? So here's 1 second, 2 seconds, 3 seconds, and 4 seconds. But now if and he's okay. I mean, he doesn't think that his clock is wrong. He just measures the time. It's okay for him. But from the point of view of blue guy, the clock of the red guy is late. Basically, he sees that when the clock of the red guy ticks 3rd second, this is a little bit later than his own clock. So 4 seconds is a little bit more later, and etc. If you will travel faster, this line will be more inclined towards the light ray. So you will see how the hyperbole are stretched here. So these differences in time will only grow. They really, I mean, something which is really hard to understand. I mean, it doesn't fit in the head, because we cannot, let's just admit it, we cannot think as a ray of light. Don't even try to imagine yourself being a ray of light. So if you are a ray of light, then your clock doesn't tick, because it doesn't cross any of these hyperbole. But anyway, the faster you are, the slower is your clock from the point of view of the person who is standing in place. And this is quite important. So this effect of the relativistic dilation of time is an effect of perception of a person from one point of view of the processes in the person which are happening in the frame of the other person who is moving. So from the point of view of the person who is sitting inside the train, the clock is ticking with a normal speed. But from the point of view of the person at the station, he thinks that this guy is late, which is which sounds right? So when we're sitting on the station, we always think that the train is a little bit late. It's because it's moving, right? But okay, this is of course a joke, right? But doesn't matter for us. So how do we know that this effect happens and etc.? So apparently it is relevant. It is very important, at least for those people who are working on large hadron collider. So these are vacuum chambers of the large hadron collider. This is a huge circle where elementary particles are accelerated to very high speeds, and this guy on a bicycle is trying to reach out to the particles, but he's too slow. So the interesting effect is happening in these tubes. One of the elementary particles causes some major problems. Is a muon. The muon is some elementary particle. We don't see it in normal life because it decays very quickly. So it decays in 1 microsecond. If I give you a muon, in 1 microsecond, it's gone. So how this particle can cause any problem to the people? Well, apparently it can, because inside this accelerator, the muons, together with other particles, they accelerated to 0.99994 speed of light. Quite fast, very close to the speed of light. And that makes it so that the lifetime of the muon from the point of view of the person in the lab, so the lifetime of the muon for the muon itself is still 2 microseconds. But recall this thing, from the point of view of the person of the station, the time of muon is dilated. So in laboratory, we see that the time has dilated 238 times. And now the lifetime as a muon is almost 1/2 of milliseconds. But in 1/2 of milliseconds, this particle travels 2.25 kilometers. So that means that this particle runs around and reaches the detector. And after it reaches the detector, I mean, if it is produced at the detector, then it flies away 2 kilometers. And only after 2 kilometers, you can see that this particle decays to something else. So that's why all the muons, they just leave the detectors in accelerators, and people have no idea what happens to them because they are traveling too fast, too far, and leave too long. All other particles, they decay inside the detector, so people can detect them and can understand more about these things. But you see, because this thing is moving so fast, its lifetime is so long, and that's why in our system, not in those, in this which is running very fast, but in our system, it lives long and travels far. Another consequence of this time dilation is what's called the Doppler effect. So the Doppler effect is actually not a relativistic notion by itself. So if you hear the ambulance coming, then when it comes to you, you see it, you hear it at a higher pitch. Then it leaves you, you hear it at a lower pitch. This is because the speed of sound is changing when it comes to you or from you. But here the similar thing happens with light, but not because there is different speed of light, but because the time between two pulses of light. So basically, if I think about this light wave as a wave, and there is a frequency of this wave, and there is some time which passes between every single pulse of this light. So from the point of view of the person who is standing still, the signal which is emitted in a moving system as a quite high frequency light signal will be delayed in the same way as every pulse, every second of time is delayed. Because it is delayed, the frequency will drop. So the light which was high frequency before will become low frequency after. Well, the light which is high frequency in the moving frame is low frequency in standing. In particular, so here you can see how the different length of light wave correspond to different colors. So if light is if the frequency of light is really high, if this time distance between the two pulses is really small, then the light is blue. If the time becomes longer, the light becomes red. What does it mean? It means that if you are moving in a car and you're approaching a red light with very high speed, so from the point of view of the officer, which keeps the red light red, your car is moving very fast and his traffic light is red. But from your point of view, this traffic light is coming to you very fast. It gets blue shifted, and instead of looking red, it gets green. So you think that the traffic light is actually green. So when the officer stops you saying that you passed the red light, you may argue that, well, you know, I was moving. So because of the blue shift, I was perceiving this light as green. So you shouldn't stop me. But then officers give you a fine for traveling for like 1/4 speed of light. Yes, so Doppler effect is the effect of the light which we perceive being shifted because the time is shifted. But this is what happens with time, but something also happens with space. We can use the same diagram and we can discuss these two people, they are still in a train, they are moving so. But the length of the train, as they think, doesn't change. So there is some distance between them. So there's a red guy and green guy. So they think that there is some distance between them. But the axis with which they measure this is the red axis, because they are sitting in a moving train. So now we can again count the number of this hyperbole, 1, 2, 3. So say they are sitting 3 meters away from each other. But from the point of the person at the station, he measures the same distance, so the distance between these two guys when they pass, and in his ruler, you see that this green line passes his measure at the point which is less than 3 meters. So from the point of view of the standing person, the moving object is contracted. So this is how your car looks when you pass at the green light. So, I mean, that's why you should never do this, because you look silly. Very good. So all these, I mean, these are strange things, like this dilation of light, the dilation of time, this Doppler effect, this contraction of length. This is, I mean, it's hard to imagine how it works, because we don't really perceive it in a normal life, because the speed of light is so huge that we never get close to this. And there is a very interesting and funny game which I really advise you to try. Those are people from MIT, and in MIT there is a game development division, of course, because it's a serious institute. Every serious institute must have a game development division. And they designed a game where the speed of light is really slow. So you can walk, and this is already 1/4 or 1/2 or 90% of the speed of light. And that demonstrates all these effects which I explained. So let me play a trailer, do an interview with these guys.
People think that relativity is extremely weird. And the reason for that is just that we do not grow up with it. And the deeper reason for that is that it only really becomes apparent when objects are moving very close to the speed of light. And in everyday life, we just don't do that.
The goal of the project was to make something familiar that was very unfamiliar. The laws of special relativity, what would they look like in a familiar setting? With the gameplay, we actually took a very familiar type of gameplay, an object collection mechanic, and made that unfamiliar. So in an interesting way, we're kind of giving players what seems at the outset like a laughably simple task, just collecting 100 objects that are visible, that are strewn around a level. There's not really much blocking you from getting them. As gameplay proceeds, though, it turns out to be a much more difficult task than you might have imagined at the beginning.
The idea of the game was that we artificially lower the speed of light. Every time that you pick up one of the little objects in the game, light gets a little slower. That means that everyday velocities, the character walking around, is becoming closer and closer to the speed of light, and thus the world around you becomes increasingly relativistic.
If it were human scaled and at walking pace, then the thought is that it would be easier for the player to get acclimated to these effects because it's really familiar, you know, like it's just walking. You walk every day. Now here it is with relativistic speeds.
We are developing this game open source. So the code that gets developed in this lab here is going to be available to anybody who later on would like to build on this. It's like a relativistic game engine. So if people would like to develop games that also are taking place in the same kind of environment, they can take what was built here and then enhance upon it and put different games into the same engine. So I hope this also appeals to other game developers.
A slower speed of light is the kind of game that I think people expect to come out from the MIT Game Lab. It's a game about physics. It's a game about something very, very complex made very tangible. It conveys some of the joy that theoretical physicists actually experience every day when they're dealing with these very, very interesting issues about the real world. So we see that games can be a very powerful medium for sharing some of the really interesting things that MIT researchers are working on with the rest of the general gaming public.
Yes. So this is, I mean, the game was developed 7 years ago, I think, but it's still there on the website. So if you go to our website, I have a link there, or you can just Google. You can download it to your laptop, and you can experience all these effects yourself. Good, but yeah. So we were talking about time and space. There are other things which are important in life. So mass and energy, for instance. And apparently from the special relativity, you can also derive a very important relation between mass and energy. I will only sketch it for you because I promised that there will be only one formula in the game. So yeah, formulas on the pictures don't count. How can we think about all this, the relation between mass and energy? So imagine that we have a teapot which is suspended in space on the orbit of Mars, for instance. And it is hot. Because the teapot is hot, it emits radiation. It emits 2 photons in 2 opposite directions with some frequency. So if we're talking about the teapot from its own point of view, where it doesn't move, then of course the frequency of these 2 photons is the same because they have same momentum pointing in opposite directions. And after this process, the energy of the teapot, it decreases a little bit because it emits some radiation. Radiation takes some energy. The energy of the photon is related to its frequency, so this is h nu. All right. And the energy of the teapot before was just some E, and then it decreases. From the point of view of the person who is looking at the teapot, which is not moving. However, suppose another person is just passing the orbit of Mars, trying to travel somewhere to Jupiter. So this guy, this red person, is moving with some high speed. So from his point of view, the teapot is actually moving. And the teapot, so before emitting these photons, the teapot has some energy and some kinetic energy. Because kinetic energy is something which is prescribed to the moving object which has some mass. So here's mass. Mass comes in the game, and here's the velocity. So, but this velocity is something completely artificial, right? So this velocity depends on the point of view. So this is actually the velocity of this red person, who passes the teapot. But also from the point of view of this person, the two of these photons are now red shifted and blue shifted. So the one which is coming towards the person is shifted to the red spectrum, and the other one is to the blue spectrum. So the frequency of one of them increases, the frequency of the other one decreases, which also depends on velocity of the observer. And the end energy will also decrease, but it must decrease with the same value, because we basically know that in the end of the day, the energy of the teapot is the same, no matter from which point of view we're looking at it. And you can make, in order to make these two points of view on the same process, I mean, this is the same teapot, it emits the same radiation. But from this two, if from these 2 points of view, I want these two processes to be actually the same process, then I need this kinetic energy to change in a particular way, which means that I need a mass of the teapot to change during this process. And that just makes and continuing this experiment, this Gedanken experiment, up to the point where the complete teapot evaporates. We can make a statement that the full energy of this teapot is contained in its mass multiplied by the speed of light square. So what is the speed of light here? It has something to do with these red and blue shifted photons. The mass has something to do with kinetic energy from the point of view of the moving person. And the energy is just the total energy contained in this teapot up to the point when it completely evaporates. So in Einstein's work about special relativity, he only mentioned that, so if the body gives away an energy in some form, well, in particular in form of radiation, its mass diminishes by particularly this volume, dE divided by c squared. So he only talked about the change of energy, but we can continue this process up to the point where the whole energy is exhausted. And it's hard to underappreciate this relation between mass and energy, because this is the core of the nuclear power. So at the moment when this formula has been written, people understood that one can extract power from the bare mass. So if you feel bored and or you want to, well, anyway, you can try to calculate how much energy is contained in your body. So if your body is, I don't know, 80 kilograms and multiply it by the speed of light squared, you will understand that this is enough for whole humanity to survive for this whole history, like, and further. Like, it's huge energy because speed of light is so huge. What happens in nuclear reactions is that one heavy nucleus breaks down into a couple of less heavy nuclei, but the sum of mass of these two product of this product of reaction, it is less than the mass of the original nucleus. It is less by like 0.1%, but this is enough to keep running all our nuclear power plants. And this is special relativity at work. Another thing, yes, so since we're talking about how special relativity is relevant to our lives, not only those people who travel at the speed of light with the rockets, etc. So a quite familiar thing, a magnet, is also a relativistic thing. I mean, we know about magnets, right? So magnets are, magnet is here actually in my microphone, or well, you name it, in a hard disk drive if you have any. But let's think about the magnetic and electric forces. So the charge, which is moving next to a wire, which has some current in it. So if the wire has a current, then this current creates a magnetic field. And in this magnetic field, the charge, if it's moving, it feels the Lorentz force and it gets repelled. So all this follows from the Maxwell laws. Remember Maxwell laws? So I started from. So we want Maxwell laws to be the same no matter what is the point of view. And now I'm going to. So it should work now. This is the moment of truth. So here's a wire. There is a magnetic field around it, predicted by, I mean, described by Maxwell laws, and there is consider a positively charged particle. I don't know, a kettle from the previous slide, which moves in this magnetic field. If it moves, then it experiences the Lorentz force, which repels it. But on the other point of view, I can also, so the Lorentz force is proportional to the velocity of this particle. So if it would be standing still, there would be no Lorentz force. So it would not repel. What if I assume, if I again assume a different point of view? And now, from the point of view of my red guy, who is always moving, from the point of view of him, this positive charge is not moving anymore because they move in the same velocity. From the point of view of this red guy, the whole wire is moving, but the charge is not. So we see that because the velocity of charge is zero, there should be no Lorentz force. But we know that it should somehow repel. So what repels this charge from this point of view of the moving observer? Apparently, when we move with the same speed as the charge, it is repelled because of electrostatic repulsion. So in the first slide, on the left-hand side here, there is Lorentz force, but the wire itself is neutral, so it doesn't repel anything electrostatically. But if we start moving together with this particle, then what happens is that these ions, which are inside the wire, they start moving because the whole wire starts moving. So these ions, yeah, so blue circles here are electrons which are flowing, and the red pluses are ions which are parts of the crystal lattice of the wire. Because the wire is moving as a whole thing, all ions are moving. So ions are positive charges. So you get a whole bunch of positive charges which are moving, but because they are moving, they get shorter. So the Lorentz contraction plays the game here. So the distance between these charges becomes shorter. So the density of them on the same length becomes larger. So this wire, from the point of view of the moving observer, it becomes, it acquires a net positive charge. It gets reddish on this picture. And because it acquires a net charge, it starts electrostatically repel the particle, which is now not moving. So depending on the point of view, the Lorentz force, the green force, turns into Coulomb force, the blue force. I mean, the names are changing, but the force is the same. So basically the same process happens. This charge moves away, is pushed away from the wire because of some force. So we see that without this really cumbersome thingy, this Lorentz contraction, we would not be able to explain this. But we know this from the Maxwell law. So Maxwell law really includes, I mean, like fits nicely into special relativity, because special relativity in some way has been built to begin with in such ways to include the Maxwell law. And it also explains why the forces which we encounter there are actually the same force, it's just the point of view is different. So that's why now in physics, we don't talk about electric forces or magnetic forces. This is a single electromagnetic force, and its effect is just different from your point of view. So we made a full circle. We started by requiring that laws of physics are the same from different points of view, like for different observers. We started from Newton, who postulated this for all mechanical laws, and that was all okay until we started thinking about electromagnetic laws of nature. So electromagnetic laws of nature must also be the same in all different points of view. That's why the speed of light must be the same in all different points of view, because speed of light is the same. There's a limit of speed, because it is only the limiting speed which can be the same in different points of view. In order to build the geometry of space and time, where there is a limited speed, we had to go through this horrible mathematics and introduce the Lorentz transformations and all this collapsing axis. From there, we saw that there are some really puzzling and strange features like Lorentz contraction and time dilation. But when we now use it, we get back the Maxwell laws as we wanted. So science works. As a comment here about GPS navigation, I told you that it was enough for GPS navigation to work just when the speed of the light is finite. But at the same time, you need to measure the time very precisely. And all these satellites are actually moving around. So they have some speeds. Their speeds are not speed of light. They are slow, I mean, relatively slow to the speed of light. But their clocks are now changing their paces. So when you want to measure time with this insane procedure, you need to take into account the special relativistic effects that the clocks on all these satellites are actually running with different speeds, different paces. And actually, special relativity is even not enough for GPS to work. These satellites are moving in the gravitational field of Earth, and the gravitation also changes the pace of clocks. And this is the effect of general relativity, which we haven't touched today, but we will touch it in 2 weeks from now. So with this, let me conclude this lecture. I hope I convinced you that special relativity is something which is really necessary for theoretical physics to work. This is only one step in our adventure to the laws of nature. And this lecture belongs to the whole series. And I really invite you to come and visit our website. We explain why now, and what do we want to say by making these lectures. And I really invite you for the next lecture, which will be happening in a week from now. Not only here, but also in Uppsala. Thanks.
Okay, questions?
I have two questions. First, the redshift. If the if the universe is expanding, then if photons get like redshifted, then wouldn't their energy diminish? So how does that work?
So, well, the energy of radiation is diminished, but why do you think it is a problem, that star? So roughly speaking, like it would be a problem if you would say that the energies must be conserved, right? But when you're talking about conservation of energy, you need to be careful and sum all the contributions to the energy. So as in this example of the kettle. So there is a kettle, there's a rest mass energy, there's kinetic energy, there's an energy of radiation. Depending on the point of view, the way you split the energy into all these components is different, but the total energy will be the same. So basically, in the frame where the star, which is moving from us, I mean, if we if we are taking the coordinate system in which this star is at rest and we are moving away from the star, it has its own energy and its own radiation, right? But from our point of view, the star is moving, so it has kinetic energy now. But the radiation is red there, so there is low energy here, but the total energy will be eventually this. Yeah, it can get confusing, and but just be sure that eventually it will work out.
And a second question is, so how does the Michelson-Morley experiments give evidence for relativity?
Thank you for this question. I must say I intentionally didn't go through all the history of measuring the speed of light. I was reading it the first time in my life, actually, when preparing to these lectures. And this is a very beautiful philosophical question, actually, how they struggled. So at the beginning of the century, the working assumption in physics was that we are all submerged in ether. Ether is a certain conjectural medium where the electromagnetic field propagates, well, where the light propagates. And what they were trying to measure is that if there is ether and the Earth is traveling through the ether, then that means that on the surface of Earth there is some total speed of ether. So we are in a wind of ether. So if the speed of light is the same only from the point of view of ether, basically it travels in ether with this speed, then we would see that the speed of light in one way is different from the speed of light in the other way. Because we assume that ether is moving. So if ether is moving, then we will see that these two speeds are different. What they measured, of course, is that the two speeds are not different. But this didn't disprove the concept of ether. Because people immediately said that, okay, fine, that means that ether is moving together with Earth. And it took many experiments and many more discussions to actually overthrow the theory of ether, because with every single consecutive experiment, it started to become more and more complex. So the ether should be dragged by any system, should stick to Earth somehow. So you start imagining more and more exclusions from the rules and more complex explanations. At this point, you should really start feeling that your concept is wrong. So the better concept is that there is no ether, but just speed of light is such a special thing, and geometry is actually pseudo-Euclidean. This is how it worked out. It was not like, you measure and everyone understands. It's harder than that, but people managed.
Anybody else?
Yes.
Yeah.
So sorry.
Actually, also coming back to ether, then I think, well, I might be wrong, but isn't it still assumed that the speed of light is the same in every direction rather than proven?
I mean, you can measure it.
Okay, I mean, maybe I'm wrong. I just heard that you can measure it's going in two directions rather than back and forth rather than going in one direction. But
well, it's it's really hard to go through all experimental confirmations of special relativity. Now people just say that hopeless. I mean, there are so many experimental confirmations of it that we just it works too well. So yeah, so you see it working every time when you watch your GPS tracker, right? And in there, light is traveling all possible directions and still works. And it works on big scales, on small scales, and everywhere. Just about ether, actually, I can say that again, theoretical physics, it is bordering philosophy. And if you are, I think the word is stubborn, but if you are really insisting on ether, it's like a conspiracy theory, basically. There's nothing wrong with that. I mean, you can keep holding your concept if you keep it making it more and more complex every time. So right now, you can still say that everything is ether, but ether has these and these and these features, and then it works out. But then you look at this thing which has this and this and these features, and you see that you've just built special relativity out of it. So ether is just all these inertial frames. And from its definition, it's indistinguishable. So in this way, you can say, you can call it ether or you can call it a space-time continuum. It doesn't matter. Yeah, now it's more fashionable to call ether space-time continuum. I wanted to, if there are, yeah, I wanted to show you this game. If I can find it. So, yeah, by the way, be careful when traveling with speed of light. There is a whole legend, and it's amazing. It might take some. So you see, there is a speed. There is a speedometer here which shows the speed on the lower right corner. So it will take some time to collect enough orbs so that we can. But you can see it already now. If I go back, everything becomes reddish. If I go forward, everything becomes purplish. Yeah, and it's interesting that if you go sideways, one part of your vision becomes reddish, another one becomes purplish. Yeah, the space-time doesn't curve yet. Yeah, but after the lecture, if anyone wants, I invite you to try yourself. At really high speeds, it becomes impossible to play. Especially at night.
Okay. More questions? Yes. So Eduardo is
well, maybe before that, also to add to your question, I think this is related. So the fact that maybe, yes, we have different speeds for like the light going in one direction and the opposite direction. I think it is related to what we call clock synchronization. So if you, as we usually assume that the light, I don't know, takes 1 second to go from here to there and 1 second to go back, so equal time. In that way, we can synchronize now the clock that stands here with the clock that stands there, for instance, over the desk. But if you assume different speeds, then you are going to synchronize the clocks in a different way. So you assume that, I don't know, it takes half a second to reach there, and then 1.5 seconds to go back. We're going to synchronize the clocks in a different way. So as far as I remember, top of my head, this shouldn't change like our physical description. So this, I think this should be independent of how you I mean, the two statements, the one-way speed of light in the two directions and the way you synchronize the clocks are kind of intertwined. So it's a bit of how you first set your clocks all over the space and how they speak with each other in some sense. But okay, now also time for the question in the chat. So there is a David Linux asking, in the derivation of the Planck's law, should the relativistic transformation of wavelengths be done before or after the derivation, or does it matter at all?
Derivation of what?
Of the Planck's law.
Planck's law.
I guess E equal to h bar mu. I guess it's not the black body, so I guess it's the energy of the photon, I assume. Or David, can you comment in the chat? That's what I understand.
Well, I mean, if we're talking about the law E equals h nu, which we didn't. So this one?
I guess so, because you had it in the slides. Wait a second, he's replying. So, oh, just a second. So, so David, you're talking about the black body radiation. So the formula for the Planck spectrum, so the curve,
what was that?
So,
yes, so that the heated body radiates, and there is a spectrum for it, and the energy of radiation is power 4 in temperature.
if I can add, he's talking about the intensity as a function of the wavelength. So
yes,
how much energy is radiated?
oh, very
per
interesting
unit,
question, by the way. So, of course, the law, when we derive it in the rest frame of the black body, right? So no one ever considers a black body which is moving in relativistic speeds. But if you ask me to do that, yeah, maybe Timo knows.
Okay, I think I can answer this because I taught it for many years. So first of all, modern derivation doesn't require to change reference frame. We're just initial reference frame, and we're happy to go. But this is modern derivation. That's not what happened in history. So historically, there was something that was called wind displacement rule, which is about how Planck formula. There was no Planck formula at that time, but was some measured formula for thermal radiation versus frequency. And using Doppler effect, which is precisely when you change reference frames, Wind told us that, well, there is certain shift depending on temperature. And this was very important to derive Wind formulas. And in Wind formulas, and this was paper a few years before Planck, appeared a constant, which is nowadays after some renormalization called Planck constant. So there is a famous statement that everything which was found by somebody else before. Well, so Wind has a formula with Planck constant inside, just as it was called differently, and was also constant inside 2 years before Planck. And to derive this, yes, he used different reference frames. But when Planck derived, and later we derived in modern way, no, we don't use different reference frame. We don't use any relativistic transformation. We're just happy in reference frame. So any more questions? So for me, so Sasha, so does special relativity teaches us that you have to run often to live longer?
Special relativity actually teaches us that if you run, your mass grows.
So it's double win, you see. You can be overweight but still live longer. So it's great.
You live longer but happier life.
So exercise every morning. So let's thank you, Sasha, again. Now let me quickly announce what will be the next weeks. So on Friday, this Friday is coming, we are going to have Ivan in Uppsala. and this will be about waves. So until now, we spoke a lot about particles, but there was symbol of Wi-Fi on Sasha's lecture today. So we are going to discuss waves very seriously. And we start with singing songs, presumably. And next Sunday, there will be lecture here about high energy physics, and we go to the elementary particles, which is like something which should move fast to make a difference, and also something is very small at the same time. So you're welcome to come to both events. So thank you, Sasha, again for today, and see you next time.